Welcome, welcome! Let's get ready to embark on a captivating adventure into the heart of a fascinating development in language technology. Today, we'll explore a groundbreaking piece of research titled Compact Language Models via Pruning and Knowledge Distillation, brought to us by the innovative minds at NVIDIA. As many of you are aware, large language models, or LLMs, have become essential tools in natural language processing, demonstrating impressive proficiency in understanding complex contexts. Traditionally, creating different sizes of these models to meet various deployment needs involves training each one from scratch, a process that is both time-consuming and demands significant computational resources and vast amounts of data. But what if there were a more efficient way to produce these models? That's precisely the question NVIDIA's researchers set out to answer. They investigated whether we could take a single, large, pre-trained model and derive smaller, equally effective models from it without starting anew each time. Their goal was to significantly reduce the computational costs and data requirements traditionally associated with training multiple models. The key techniques they employed are known as structured pruning and knowledge distillation. Allow me to elaborate on these terms for clarity. Structured pruning is akin to carefully trimming a tree to enhance its health and growth. In the context of neural networks, it involves systematically removing entire components of the model, such as neurons in feed-forward layers, attention heads in the transformer architecture, embedding channels, and even entire layers of the network, referred to as model depth. By eliminating these redundant or less significant parts, the model becomes smaller and faster without substantially compromising its performance. The researchers didn't approach this pruning process haphazardly. Through extensive empirical exploration, they discovered the most effective strategies for pruning along each of these axes. For instance, they found that initially pruning neurons and attention heads yielded better results than also pruning embedding channels. However, after implementing some retraining, incorporating pruning across all components led to superior performance. They also observed that pruning the width of the model, reducing the number of neurons in each layer, was more effective than pruning its depth, reducing the number of layers. But this held true only after the model underwent retraining. Now, simply pruning the model isn't sufficient, as it can lead to a loss in accuracy. This is where knowledge distillation comes into play. Think of it as a mentorship between the original large model and the smaller pruned model. The larger model acts as a teacher, and the smaller model serves as the student. By learning from the outputs of the teacher model, the student model can regain and even enhance its performance despite its reduced size. What's particularly noteworthy is how efficiently they were able to retrain the pruned models. By leveraging knowledge distillation, they retrained these models using less than 3% of the original training data. In terms of computational effort, deriving the smaller models from the large one required up to 40 times fewer training tokens compared to training each model from scratch. For the entire family of models, this approach resulted in a compute cost saving of approximately 1.8 times. The outcome of this process is the MINITRON family of models, compact versions of the original Nemotron 415B model. The MINITRON models come in sizes of 8 billion and 4 billion parameters, still substantial, but much more manageable than the original model. But how do these smaller models perform? According to the researchers, the MINITRON models demonstrated up to a 16% improvement in MMLU, Massive Multitask Language Understanding scores, a benchmark used to evaluate a language model's comprehension abilities compared to models of the same size that were trained from scratch. They performed comparably to other community models such as Mistral 7B, Gemma 7B, and Llama 3.8B, and even outperformed state-of-the-art compression techniques documented in other studies. This research provides valuable insights into the process of compressing large language models. It highlights practical methods for combining different pruning strategies and effectively retraining the models with minimal additional data. By applying these techniques, we can produce a range of language models tailored to different deployment scales without the substantial costs associated with training each one from scratch. In essence, NVIDIA's work offers a practical roadmap for scaling language models efficiently. It demonstrates that through thoughtful pruning and knowledge distillation, we can maintain high performance while significantly reducing resource requirements. This advancement has important implications for making advanced language technology more accessible and sustainable. Thank you for joining me on this enlightening journey into the world of compact language models. Until next time, keep exploring and stay curious.